So I've been giving this class a lot of thought, and for whatever reason, I'm not sure exactly what it is. That's what I'm going to talk about a little bit. This just hasn't been going as well as I'd hoped. I've cut some material out. We're a full, and this, this isn't directed at everyone, but we're a full 2 days behind where I've ever been in the last 3 years in this class yet. I don't get the sense people are getting it. In the last homework, there's one problem from the book that essentially nobody got. It's a material I was covering at the end of class last time, and I was in the middle of a sentence, and people just got up and walked out. No respect at all. Didn't even let me finish the section. I let you go early. You could stay a minute or two late. Let me finish the section. I think part of it is the way I tried to set the tone of the course at the beginning, so it's partly my fault. People that come and take out their computers and watch movies and play on the internet or play on their phones, that's your fault. You're probably not getting what you need to get. You're not getting anything out of this course. But for others, it's, I tried to set a tone in here that you need to come, you need to work, you can't talk, you can't play around. I'd appreciate you not disturbing other people, getting up and leaving. And the signal I was trying to send is this is going to be a hard class. You need to do the work, keep up, do it every day. And if you don't do that, you're going to fail the midterm. Clearly, people didn't take that to heart. Clearly, the kind of work, you look at the correlation between missing homeworks and failure on the midterm, and it's way over 60% at least. So people really aren't doing the work they need to do. Somehow I didn't set the right tone, and something's just not quite going right. I think one thing it probably is the size of this course. I taught this one time before. It had 400 people at UC San Diego. That didn't go very well. 400 people is too big for this course. Here I've never taught it with more than 60, and most of the years I've taught since I've been here, it's been about 40 people. You get about 20 coming to class, and people don't walk out on you and you have some sort of a personal connection that you don't get in these big classes. They come to your office hours for help. No one got the problem right. No one even tried to make an appointment. No one came to office hours. No one asked a single question in email about the problem. There's no personal connection between me and you. And that's probably the size of this class. That's my conclusion. That's what I'm hoping. And probably my errors at the beginning in being sort of a hard ass and trying to send signals that you needed to work hard. And I probably set the wrong signals. And it was more off-putting than helpful. And so I've learned something too from that. You try things. I did this at San Diego. It was 400 people. I thought, okay, I got 100 people in here. I'm going to have to, make it so it's a learning environment, and I failed to do that. But I also think the size of this class is a real inhibition to learning. I don't think there's any personal connection that develops to a large part between us, and it just really hasn't worked very well. So I'm the one who schedules these courses. I'm going to push really hard. It's not my call to reduce the size of this course in the future. I think this is just too big. Some of you are too far away. I can't even hardly see your faces to really get any kind of connection with you and to have the kind of learning that we need. So, I apologize for whatever my side of this and setting the right tone for this is, but the hardest part of this course, I think, is over. It's conceptually difficult. We've got some theoretical things ahead. I'm not going to say it's easy from here on out because we've still got some work to do. But the really hard estimation part is really over for the course. It's really conceptual. And now is a time when there's time in the next 3 weeks. I don't really plan to do much the last week. I'm going to review the last day of class, I decided, just to try to help. I'm not going to do a whole lot the last week of class to give you a chance to get your projects done so there's not new material coming from the class on top of the projects. I'm going to have guidelines for how to write up your projects. I'm trying to give you benchmarks to keep you on track. But we only have a couple of big topics left. I'm going to try to take them slow. And then in the last week, not give you a lot of new material to give the people that need a chance to catch up the chance you need. So it's not too late to catch up in this course, but you're really going to have to do the work. Finally, one thing that happens in these courses, and I had this happen in both directions, sometimes a couple of faces in the course draw your attention and you conclude a lot from a few people in the course, and it can really mislead you from a small sample. One time in history of thought class, again at UC San Diego, I thought it was going great. Because one person in the class was smiling and asking lots of questions, and it was, I thought, okay, this is going wonderfully, but the evaluations were some of the lowest I ever got. So I was like, oh, okay, I need to pay more attention than just one person. And sometimes the other thing happens too, you get people really unhappy, and it kind of they're hard to deal with, and it just makes you sour on a course a little bit, but it's really not a good view of what the overall course is. So my hope is that that's what's going on to some extent here, that things are actually going to a large extent better than I think, that you are getting this material. But for those who aren't, stick with it, do the work you need to do, and particularly all of you, because you're the ones I'm the most worried about. Get your butts to class and do the work you need to do, and let's get this right so that I'm not in the position having to decide to have to fail you. Because I can't pass you if you don't do the work and if you don't know what you need to know to go forward. And I'd really, really, really not have to make that choice. I hate it. I hate failing people. It's the worst part of this job. It makes everyone unhappy. It makes me unhappy. It makes you unhappy. And so I'll do my best to make it so you can pass this course, but you're going to have to do your part too. And there's plenty of time left to get that done. So, all right. And I ordered the song to play now. I just needed to get that out. It's been bugging me. I've been thinking about this night and day for the last week and a half. And just, what do I do? What do I do? What do I do? So I decided just to say what I think. And I could have this completely wrong, but that's sort of how I'm seeing things. I think it's mostly a size problem, my own view.
You said you were going to give an outline of how you want the paper to be set up.
Yeah.
I saw you had some from previous years.
Yeah, it's going to be exactly the same. I'm going to cut and paste. So if you go to the sidebar, there's some project links. It's right there. If you want to get started on that, those guidelines will be identical. Same with the homework. So I'm going to be giving the same homework. So if you want to move ahead, what you'll see is there's only 2 more problems, and the rest of the homework is do your project. So most of the homework now is going to taper off a little bit, but I have to give enough to help you learn the material in the class. So there's a couple of problems, but not very much. Okay, we were talking about simultaneous equations. What happens when you have more than one equation to estimate? And what happens when these are structural equations, meaning that we can have endogenous variables determined within the system on both sides of the equation. So we talked about the nomenclature. It's not really the word I was looking for, but there's reduced form, there's structural models, there's behavioral equations, there's identities, there's technical conditions, there's equilibrium conditions, all the various types of equations. Now we want to get a little more into the econometric issues. And I want to look at what's called simultaneity bias. The reason why we have troubles when we have more than one equation, when we have simultaneous equations. So this is called simultaneity bias. And so the one we didn't finish last time is we started with this model. So we had an X and a Y. And those are both endogenous. So there's just one exogenous variable in this model, and that's the constant. Oh, there isn't any. There's just the shocks are the only exogenous things determined outside the model. These are just drawn from some distribution and tossed into the problem. So these are the only exogenous things. Now, in order to analyze this, we need to know about its reduced form. So what we do is just substitute one equation into the other. So I just take this x, put it in there, solve for yt. So I get yt is 1 over 1 minus alpha beta times alpha vt plus ut. So that's the reduced form equation for yt. We've eliminated the endogenous variable on the right-hand side. That's purely a function of things determined outside the model. In this case, just the shocks. If I had any exogenous variables in here, and we'll do an example like that next. I'll do the example from the book. This is supposed to be simpler than the book's example to make it easier to see. So if I had any other exogenous variables or a constant, they'd be in here too. But in this case, they're not. We can do the same thing with xt. You can either plug this into that y there and solve for x, or you could just plug one into the other. But similarly, if I can spell it right, xt should be 1 over 1 minus alpha beta times beta vt plus, yeah, that's it, beta ut plus.
1 minus alpha beta times beta ut plus vt. It's completely symmetric. So those are the reduced form equations. And we can use those to analyze what happens. Now we can see the problem right now. Now that we have the reduced form for x, the problem's easy to see. We know that if x, we're going to imagine, what we want to know is what if we were to run this regression, regress y on x, or we could do this one, we get exactly the same answer here, just we'd get betas instead of alphas. But suppose we run this regression, what's the problem? Well, xt, you can see, has ut in it. So ut is part of xt. So because this has ut and ut is there, those are correlated. And we know whenever they're correlated, we have bias. So that's the simultaneity bias. When you have simultaneous equations like this, you're going to get that kind of a bias. This equation, this x, will pull in the y, and the y has the u in it. So it's the simultaneity that does it. And you can see if you ran this regression, x on y, you'd have the same problem because y has v in it. And so this regression would have trouble too. Yes, sir?
What happens to yt? You have yt equals alpha beta yt plus v.
So I took, this is the same as yt minus alpha beta yt. So that, I'm just taking that times that, move it to the other side. And that equals alpha vt plus ut. So then I take yt times 1 minus alpha beta equals alpha vt plus ut. You with me? So I just multiply this out, move this to the other side, factor out the y, then divide through. I shouldn't do this in my head. So if you were to run this regression, xt would have ut in it. Problem. Similarly, if you run this regression, yt, you can see, has vt in it. They're correlated, that's a problem. So both of these regressions would give you biased estimates. We'll just focus on this one. Because, as I said, this is just switch x and y and alpha and beta, and you'll get the same answer. It's completely symmetric. So what we want to know is then what happens is there any bias? Is a better way. Let's say it this way. Is the estimate consistent? That's what I mean by what happens. If you regress y on x, as in that first equation. So the equation we're running is yt is alpha xt plus ut. And we know that alpha hat is the sum of the xi minus x bar times y minus y bar over the sum. So we just need to evaluate that, and we're done. What are they talking about? Can't hear him, but passion. I had the same passion, I was just quieter. I just divided by 1 over n on the top and the bottom so I can take a p-lim. What's the p-lim of this? What's this an estimate of? Starts with a C, covariance, and this is an estimate of? So you're starting to recognize those forms. Good, good, good. It's good. So the p-lim of alpha hat is the covariance of x and y over the variance of x. That's always true. Now the one we've been using that the p-lim of alpha hat is alpha plus the covariance of x and u over the variance of x. We've mostly been using this form to evaluate the bias because it isolates alpha, and then you can just say, well, if this is 0, there's no inconsistency. If it's non-zero, no inconsistency. My double negative there totally threw me off. If this is 0, it's consistent. If it's non-zero, it's inconsistent. And so this is an easy form to work with for the most part. We could work with that easily here. What's the covariance of x and u? So it's the covariance of this thing right here and ut. What's the covariance of those two? They're assumed to be independent. So the covariance of that and that is 0. Well, those are going to be related, right? So this is going to be beta over 1 minus alpha beta sigma squared u. You see that? So the covariance, we can do it this way. I think that's how I was doing it last time. You can do it this way too. You can look at the covariance of x and y here. Those two terms will intersect, those two terms will intersect, and you can look at the variance of x. So I could also use this formula, but I'll use this one since that's the way we've generally done this. So to evaluate that, we need to find the covariance of x and u. And this seems to be where people have the trouble. So just always plug in for x. So it's the covariance of, well, what is x? It's 1 over alpha, 1 minus alpha beta times beta ut plus bt and ut. Those brackets just leave it. And then just to do all the steps, this is the covariance of 1 over 1 minus alpha beta times beta ut and ut plus the covariance of 1 over 1 minus alpha beta bt and ut. So I just multiplied that times that and that times that. I just separated the two terms. Okay? All right, I got heads going in the right direction today. I'm liking that. Yes, yes, yes. And we assume u and v are independent, uncorrelated. So what's this covariance? Correlation?
0.
0. So this one's 0. And this will be, oh gosh, there's all these rules that you just, because you had cheat sheets aren't in your heads, and now when you need them, you don't know where to get them. But the covariance of A, X, and Y is A times the covariance of X and Y. That's what I'm going to use here. So this one's 0. This is beta over 1 minus alpha beta times the covariance of ut and ut. And what's that? So I just pulled that out. That's A. Covariance of something with itself is the same as the, starts with a V, second letter's A, Variance. So this is the variance. So this is beta over 1 minus alpha beta sigma squared u. So we need that. So we know one part of this. This is beta over 1 minus alpha beta sigma squared u. So we know this part. Beta over 1 minus alpha beta sigma squared u. So that's the top part. Now we need the variance of x. What's the variance of x? So the variance of x is the variance of beta 1 over 1 minus alpha beta times beta ut plus dt. Which is 1 minus alpha beta. This is like the covariance of AX and AX, because it's, never mind, I was going to try to relate it to what we just did, so you get an A squared. Never mind, that's going to make it harder. No. If you got what I just did, wonderful, and you really get this. If not, just flush it. Okay, so this is, I'm just pulling out the constant times the variance of beta ut plus vt. What's the variance of this? So this is 1 over 1 minus alpha beta times the variance of beta ut plus the variance of vt plus 2 times the covariance of beta ut and vt. I'm doing everything in explicit detail today just to try to help. That's the formula for the variance of a sum. The sum of the individuals plus 2 times the covariance. What's the covariance of u and v?
0.
It's 0. This is sigma squared. What's the variance of v? Another name for that is sigma squared v. Variance of v.
Is the first part still squared? The 1 over 1 minus alpha beta?
Yes, thank you. That could be confusing, thank you. Sorry if that threw you off. And this is beta squared, sigma squared u. And you still get 1 over 1 minus alpha beta squared. So now, this is the other part we need. So this part down here,
Can you explain where the beta square came from?
sure. It's the variance of beta ut. And so that's the variance of ax is a squared variance of x. So it's this beta here, when you take the variance becomes. What I was going to say a minute ago is it's just that covariance rule. Because if you take the covariance of ax and ax, you have two, that's the variance of ax. That's the same as the variance of ax. So you get two a's, you get an a squared out in front. But that's kind of a, it's easier to appeal to the definition. It's the expected value of x minus x bar squared summed up. Because you're squaring the things in the middle, the constant gets squared and pulled out. So it's from that expectation. The definition of the variance is the expected value of, in this case, it would be bx minus bx bar squared. When you do this one, or bu, sorry. So that's what this one would be. And because of the square there, the beta gets squared when you pull it out.
So what is this all for? Like, what is that?
Okay, now, so let's put it all together. So now we know that the p-lim of alpha hat is alpha plus the covariance we know is beta over 1 minus alpha beta sigma squared u, and the variance is this. 1 over 1 minus alpha beta squared times beta squared sigma squared u plus sigma squared v. And now there are two important messages here. But let me write this in another way so that the messages can be received more easily, easier. Some word I'm looking for, fill it in. This will be plus beta times 1 minus alpha beta sigma squared u over beta squared sigma squared u plus sigma squared v. I just flipped that over and multiplied it on the top. Fraction on the bottom, you flip it over and multiply by the top. Remember that rule? Just took this thing, flipped it over, multiplied through. I've got a square here, so I'm left with a 1 minus alpha beta on top because it cancels that one. You get that. So 1, it's inconsistent. Because this is non-zero. And so this estimator is inconsistent. Now, I did this in a lot of steps. If you do enough of these, if you go through enough of these and start doing them, you'll be able to look at this and just write down the covariance very fast. You can just look at the solutions for x and y and write this one down. So we could have done this problem in 30 seconds if you know how to do the covariance and the variance. That's where you're getting hung up. And once you get that down, you can just look at, okay, there they are. Write this down. Then you get that it's inconsistent. 2, unless beta equals 0. Because if beta equals 0, what happens to the top term? It becomes 0. And the bottom, that becomes 0, but we still have something left because we don't want 0 over 0. We don't like 0 over 0 because you don't want to take L'Hopital's rule. So we get 0 over something, which is 0. So if beta equals 0, then it's consistent. So what we're saying is that in this system, it's the simultaneity that causes the bias. Because we have xt is beta yt plus vt. If we get rid of that term, if beta equals 0, we no longer have simultaneity. Xt is just vt. You don't need yt to determine x. You need y to determine x, x to determine y, so it's simultaneous. It's a simultaneous system. This is like supply, quantity, price, price and quantity, supply and demand. It's the same kind of a system. If you can get rid of that term, if you no longer have simultaneity, then you get rid of the bias. The minute beta is equal to 0, it's no longer biased. So what we're trying to demonstrate with this problem is the simultaneity bias. show you that when x and y are jointly determined, when y determines x and x determines y, we have joint determination, you get bias. And the reason is that, again, y is going to have u in it. The minute you put y in x, it pulls this error in. Y has u in it, so you get a ut here, so x is going to be a function of u and v. If this term isn't there, that ut never gets yanked into this equation, and you don't have anything to worry about. There's no bias. So it's the fact that that beta is non-zero. Similarly, beta would be inconsistent unless alpha was 0. Those are called recursive systems. You determine x, and you use x to determine y, and you can go on. But anyway, don't worry about that name. So these estimates are both biased and inconsistent. Now I'm going to do the book's example, and just do this one more time, the way the book does it, and then we'll move on to identification, something else. So got this? That's one thing that should be seared in your heads already. And the variance of a constant, C is some constant. It's not a random variable. This is 11.38. Plus AX is the variance of AX equals A squared as the variance of X. When you add a constant to a distribution, all you do is shift it around. You move it back and forth, but you don't change its distribution. You don't change the variance. So this says adding a constant doesn't change the variance. This is the result here. So when you have constants in the problem, you're going to have to evaluate variances sometimes. The constants don't matter. All they do is take the distribution and shift it. If you've got, this is a mean, there's the mean plus a constant. But it doesn't change the spread, it doesn't change the variance. So adding a constant doesn't do anything. Multiplying by a constant squishes or expands this. And that's why this, adding a constant doesn't change the distribution at all. Then the other one we've been using is if the covariance of AX and BY is AB, covariance X and Y. I've been using those results over and over, assuming you know them, but now I'm realizing, or have finally realized, I suppose, maybe I should have put these down earlier. Those rules should be helpful. That's all we do every time we use these problems, is we apply those. Those are the rules I've been applying again and again and again and again to get the answers. That's it. So in the last problem here, we know that alpha hat is the covariance of x and y over the variance of x. We know that xt is 1 over 1 minus alpha beta times beta ut plus vt. And that yt is 1 over 1 minus alpha beta times ut plus alpha vt. Let me check this. I don't think this is right. That's right. Those are the same formulas we had earlier? Did I write them down right earlier? Okay. So what's the covariance here? What's what's the variance of this? What's the variance of x? Well, it's just, there's no covariance here, so it's just beta squared over 1 minus alpha beta squared sigma squared u plus that squared sigma squared v. So hopefully you can just get to where you just look at these. The covariance is going to be this times beta sigma squared u plus alpha sigma squared v. So once you learn how to do this, you can just write these down. Okay, this is 1 over 1 minus alpha beta squared times, well, it's going to be that times that, beta sigma squared u plus that times that, alpha sigma squared v. And all the other ones, that times that and that times that are going to be 0, so I won't bother with them. And the bottom is just 1 over 1 minus alpha beta squared times beta squared sigma squared u plus sigma squared v. Just using that equation. And if you work, these things cancel. And again, you see that if beta is 0, you get alpha sigma squared v over sigma squared v, so you get alpha. So what's required is that you have beta be 0. So I'm just pointing out, it doesn't take a half an hour to do these problems once you learn how to do them. It takes 15 seconds. And that's part of my disconnect with you all. I need to remember where I was at your age, that it doesn't take 15 seconds. It takes 20 minutes for you to go through these, and I need to go slower. I'm trying. This is actually the same answer as over here. I worked it out. I proved it last night. There it is. Here I used the covariance of x and y over the variance of x and did it that way. The other time I used alpha hat as alpha plus the covariance of x and u over the variance of x. So I did it two different ways. But you get the same answer in both cases. All you have to do to get this answer is just add and subtract alpha and play around with the terms. All right. Now let me do the book's example of simultaneity bias, and I'll try to do it a little quicker so that we can see how this works in a little more general context. So they try to model inflation. Okay, so P is beta 1 plus beta 2 W plus UP. So this is the error. This is the wage growth, wage inflation. This is price growth or inflation. So these are in growth rates. So this equation is saying that that cost push inflation is feasible. This is modeling cost push inflation. It's saying when wages go up, that drives output prices up. You know how that went well. In a competitive model, the real wage, W equals price times marginal product, so W over P equals marginal product, so you could use that. But never mind, I won't go through that. Now there's another equation that says W, wages, equal alpha 1 plus alpha 2 times inflation plus alpha 3 times unemployment plus UW. Alpha 3 here is less than 0. When unemployment goes up, we think wages go down. So this is the wage equation. This is the wage setting equation. So wages are set according to the unemployment rate, according to prices, and quite honestly, I would have added productivity to this. But we don't want to have too many variables because then it gets so we can't do the math. So we have simultaneity. Wages cause inflation, and inflation causes wages. That's called the wage price spiral in your textbooks. They call it a spiral rather than simultaneity, but it's the same thing. One drives the other, drives the other, drives the other. If I just put a t minus 1, I could iterate back and forth in this. But we're just doing it at the same time period. But there's a simultaneous determination of wages and prices. So in this model, the unemployment rate's the exogenous variable, and wage growth and price growth, wages and inflation are the endogenous variables. The constant's exogenous as well. So we have exogenous shocks, an exogenous unemployment rate, and then a couple of constants. So the reduced form should depend upon the constants, the unemployment rate, and the shocks, the non-endogenous variables. So the reduced form always depends upon the non-endogenous variables, and again, W and P are endogenous. So how would I eliminate W from this equation? I'd take this equation, sub it into there, right? And then I've got price as a function of price and exogenous things. Move that thing to the other side, and then solve it. And so the reduced form for price, if you do that, is that price equals 1 over 1 minus alpha 1, beta 2 alpha 2, beta 2 alpha 2, yep, beta 2 alpha 2 times beta 1 plus beta 2 alpha 1 plus beta 2 alpha 3 times the unemployment rate plus the shock, beta 2 UW plus UP. So you see what I did there? Just plug that into there and then solve for P. That's all there is to it. To get W, I could either plug the price solution into here and solve for W, or I could plug this into there and solve for W. But the wage solution here is somewhat similar. Alpha 1 plus alpha 2 beta 1 plus alpha 3 UN plus alpha 2 UP plus UW. So to do these problems, these simultaneity bias problems, what's the first thing you do? You take the system of equations and find the reduced form. That tells you what shocks are in each variable. The reduced form is going to tell you what shocks are in each variable right away. And so if I ask about the bias on a test and you go, oh crap, I got to do that math stuff, or what do I do? At least be able to do it intuitively. Tell me, okay, if I run this regression, beta 2 hat is going to be biased. Why is it going to be biased? Well, if I look at the reduced form for wage, I see that UP is in it. So the wage is correlated with UP. When UP goes up, this goes up by alpha 2 over 1 minus beta 2 alpha 2. They're correlated. They move together. And so since these are correlated, it's inconsistent. It's biased and inconsistent. If you can't get to the reduced form, you can at least say, well, P has UP in it. See that? Well, that has UP in it. So that has UP in it. So that has UP in it. So these are correlated. So there's bias. So you can still rack up a few points. Not full credit, but you won't walk out with a 17 that way. So the math is a vehicle to allow you to understand that. Now we can use the math to talk about the exact bias. What is the exact bias? That's what the math tells us. But intuitively, we already know there's bias here. Now I want the exact bias. How do I find it? So suppose I run that regression over there. How do I find whether it's inconsistent or biased? in this regression, what's beta 2 hat equal? What's the p-lem of beta 2 hat equal? It's beta 2 plus
Covariance over variance.
the covariance. Yes, thank you, or the variance. So the variance is the thing that plays the role of x in this regression. Starting as x is w. So this is the variance of w. And we get that from this equation. This is an exogenous, it's going to be, that's a constant, so that's not going to affect the variance. So it's going to be that over that squared, sigma squared un, that over that squared, sigma squared up, sigma squared u over times that squared. So the variance of w is just the square of this thing, basically, without the constants. And then what goes on the top? Covariance of the thing playing the role of x and the thing playing the role of u, which is u is playing itself. It wants to make sure it can tell us from its sister u, w. So what's this covariance? Well, you look at this equation in UP and you say, oh, those are independent. Unless I tell you things are independent, unless I say otherwise. Oh, those are independent. Oh, there's an intersection. So this is going to be that squared over that squared times sigma squared UP. Will be the covariance. I mean, importantly, it's not zero. This is non-zero and this is non-zero, so there's inconsistency. Now let's work out the exact amount of the inconsistency. So this is beta 2 plus, so the covariance of W and UP, I could go through all the steps and multiply it out. I'll get alpha 3 times that, and so on. But all those inner product terms are zero, except the one that intersects here. So this is going to be alpha 2 over 1 minus beta 2 alpha 2 sigma squared UP. Can you just look at that and kind of see that now, by any chance? A few heads saying, yeah, not as many as we'd like. But that's not the empty set either, or the empty head, or whatever we're looking for here. If not, you're going to have to take the covariance of that whole expression. So you would plug in this, so it would be the covariance of that whole expression in UP. Then you'd start multiplying. UP times a constant. Oh, there's no covariance with a constant. That's zero. The covariance of UP with UN. Oh, there's no covariance there. The covariance of UP with UP. Ah, that's the covariance of alpha 2 over 1 minus beta 2 alpha 2 and UP. That's that. And then the covariance of that and that, oh, that's 0 too. So the only thing you pick up is this term. And the constant is that. The variance is just the covariance of this with itself. So you just square it. Still multiply it together, but you're multiplying by itself instead of UP. Now multiply it by itself. Well, you're going to get squares wherever the constant won't matter, but you'll get an alpha 3 squared over that squared, sigma squared UN. An alpha 2 squared, sigma squared UP over that squared. So when you square these out, you'll get a bunch of cross product terms, but those are all zero because all the things are independent. All the shocks are independent. And so the only one you really pick up is this one. Well, you pick up each one with itself, sorry. So you get that squared, that squared, that squared, and that squared. So this is going to be what we say the covariance was? Alpha 2 over 1 minus beta 2 alpha 2 sigma squared UP divided by, so that's the covariant, I hope. I should look at my notes, huh? That's why we do them. Alpha 2 sigma squared UP over 1 minus alpha 2 beta L. But L's a mistake, that's a 2. Yay. Yeah, we got it right. So the variance is of W is what? 1 over 1 minus alpha beta 2 alpha 2 squared. That's the term in front. Times alpha 3 squared sigma squared UN plus alpha 2 squared sigma squared UP plus sigma squared W. I could cancel one of these with these, and we get something that looks just like we got before. If you flip this over, it'll cancel one of those, and you'll get 1 minus beta 2 alpha 2 times alpha 2. Just like we had, same form we had in the last problem. Should be. But again, what would it take not to have simultaneity here? Well, alpha 2 would be 0, right? If alpha 2 is 0, W is just a function of exogenous variables. There's no simultaneity. W doesn't need P to figure out who it is. Here, W has to know about P before it knows its own value, but not now. So if alpha 2, but if alpha 2 is 0, what happens in this term? It's 0, right? We get P lim beta hat 2 is beta 2 in that case. So when there's no simultaneity, once again, we get the right answer. When there is simultaneity, when there's joint determination of W and P, then you don't have. Let me just explain something here that maybe will help. So when I say simultaneity, it's like x plus y equals 3, x minus 2y equals 4. I have to solve these two equations. These are simultaneous equations. I have to solve them jointly to get the answer. But if I have x plus y equals 3, and this is 0, and x equals 4, now I don't need y to figure out what x is. I plug it into here, and then I get y. That's the way these systems work when alpha 2 is 0. W is just a function of exogenous things like 4. That's an exogenous thing. And then you just plug it into the other equation once you know what it is to get P. And you don't, this doesn't ever pull in the shock from the other variable because it's not there anymore. This term is not there anymore. And so that gives you a system that's just like this. It's recursive. You solve this, then you solve this. This is simultaneous. So once you get into these recursive systems, if we have x plus y minus 3z equals 4, x minus 2y equals 8, and then z, x minus 2z equals 8, and then z equals 4 again. This is a recursive system. You find z here, plug it in there, get x, then plug x and z into here to get y. There's no simultaneity in this problem. These kinds of systems are not going to have biased estimates because they're recursive. But if I make it a fully simultaneous system, x, y, and z is in every equation, then we're going to have simultaneity bias in the problem. So when you get these recursive systems like this, that's really what you're doing here. You get rid of the problem. But intuitively, you're just taking away the thing that puts UP into W. So P has UP in it, And that's how it gets into W, so you just take that away. All right, enough of that. New topic. Actually, let me ask for questions on the old topic. So we've done simultaneous equation. We've talked about how to talk about them. The words we use, simultaneous equations, reduced forms, all that sort of thing. We've shown the econometric issue involved with simultaneous equation, its inconsistency. Now we're going to talk about what to do about it. And what to do about it is two-stage least squares. So we've done OLS. When you did heteroscedasticity, I didn't call it this, but you basically did weighted least squares because you weighted by the variance, by the standard deviation. So we could have done those by using weighted least squares, but I made you do it a different way so you'd understand it. But that was just weighted least squares. We've done instrumental variables estimation as a solution for correlation between the error and the right-hand side variable. Two-stage least squares is a form of instrumental variables estimation. It's equivalent to instrumental variables estimation, but it's a special case. So where we're headed next is to learn how to estimate these things. In eViews, it's really easy. We'll just be using that second box again for two-stage least squares, and I'll show you how to do it. It's trivially easy to do it. But we need to understand the issues. And one of the key issues for estimating these models is something called identification. So we want to start talking about the identification issue. In this problem, although we cannot estimate the structural equations because we have this endogeneity bias, it's also called endogeneity bias, the simultaneous equation bias, we could, though, estimate the reduced forms, because the reduced forms just have exogenous variables on the right-hand side. So if we estimate the reduced forms of OLS, those estimators are best linear unbiased estimators. They're blue. Because if you look at the reduced form for these two, I erased them now, but this was just a function of the unemployment rate, a constant in errors. This is a function of the unemployment rate, constant in errors. So the constant and the unemployment rate are exogenous variables. So we just have endogenous on exogenous, and there's no problem with estimating those at all. So we can estimate the reduced form equations without any trouble once we know what they are. But then the identification problem is, can we use those reduced form parameters to recover the structural parameters? Suppose I want the elasticity of demand, which is in the demand equation. So I've got everything measured in logs. The log of price is A plus B log Q plus an error. That beta is going to give me an estimate. I can't remember if I got it 1 over beta or beta, but that'll give me an estimate of the elasticity. And so, but when I estimate the reduced form equations, I don't estimate beta, I estimate something else. And so the question is, for identifications, can I identify that beta I'm interested in from the estimates of the reduced form equation? Sometimes these models will be under-identified, you can't do it. Sometimes they'll be exactly identified, you can do it. And sometimes they'll be over-identified. You can do it, but there's more than one way, and we'll have to figure out which one to choose. So let's start looking at the identification problem. And we can understand this graphically, which is nice. I hope. So the first one I'm going to show you is a model that's not identified. So let's take, this is model 1. QD equals alpha naught plus alpha 1p plus u. That's demand. Obviously, there's a little d up there. I think you probably knew that, but oh well, in case not. Beta 0 plus beta 1p plus v. That's supply. And then QD equals QS. And we'll just call it Q is equilibrium. thinner than the hotel I stayed in this weekend, which I didn't think was possible. We can work out the reduced form. How do you do that? Impose this, those are both Q's, right? Set them equal and solve for P. Take the solution for P and sub it into either equation and solve for Q. So if you solve this, you'll get P is beta 0 minus alpha 0 over alpha 1 minus beta 1 plus 1 over alpha 1 minus beta 1 times V minus U. And you'll get Q, well, let's stop there. So this regression, we can write this as P equals lambda 0 plus E1. So this term here is E1, and that term there is lambda 0. So if we run this regression, we basically run price on a constant. And then we have an error. Turns out when you run a variable on a constant, you just get the mean of the variable. So the estimator here is just P bar. But I'll come back to that in a second. If I plug this solution back into one of these equations, you'll get Q. So that Q is equal to alpha 1 beta 0 plus alpha 0 beta 1 over alpha 1 minus beta 1 plus 1 over alpha 1 minus beta 1 times alpha 1v minus beta 1u. And I'm going to call that gamma 0 plus beta 2. So those are just the reduced form equations from solving the system. Those are the solutions to that system. You're solving for the dot where supply and demand intersect. It's just the solution for price and quantity. This is a model where you have demand is a function of U and supply is a function of V. And so the solution for price and quantity are going to depend upon the values of V and U. That's what we're seeing here. And the constants that are built into the system. If we were to estimate this, we would just run, so to estimate the reduced form, you would just run P on a constant. And you would run Q on a constant. That's what these regressions, there's no X's here in these models. Turns out in that case that the estimator, when you do that, you're going to get lambda 0 hat. It's just P bar. Doesn't matter if you see that or not. You get lambda 0 hat out of this. For the Q equation, you're going to get gamma 0 hat. And that turns out to be Q bar. But again, if you don't see that, just realize when I run this regression, I'm going to get two pieces of information. I get gamma hat and I get lambda hat. Here's the problem. How many structural parameters are there? There are 1, 2, 3, 4. So I have 4 unknowns. Alpha 0, alpha 1, beta 0, and beta 1, and 2 pieces of info. I only know gamma 0 hat and lambda 0 hat. So I have 4 unknowns, alpha 0, alpha 1, beta 0, beta 1, and just 2 pieces of information. See, gamma 0 is a function of all 4 things, alpha 0, alpha 1, beta 0, beta 1. Gamma 0 is a function of all 4 things too, beta 0, beta 1, alpha 0, alpha 1. So I've got 2 equations that relate the estimates, these 2 things, to these. But if I only have 2 equations, I've got 2 equations. I have this equals that, and that equals that. I've got 2 equations and 4 unknowns. There's no way to solve that. This is an under-identified system. There's no way to take 2 pieces of information, 2 equations. What I know is that lambda 0 hat is beta 0 minus alpha 0 over alpha 1 minus beta 1. So that's one equation. And 4 unknowns. So that's like, this is a number you get. This is 7.5 equals 4 unknowns equals x plus y plus z plus w. Find x, y, z, and w. You can't. Then you've got another equation, gamma 0 hat equals that one. Alpha 1 beta 0 minus alpha 0 beta 1 over alpha 1 minus beta 1. And again, so you have 2 equations, 2 pieces of information, 2 equations and 4 unknowns. You can't solve that system. You can't solve it uniquely for alpha 0, alpha 1, beta 0, and beta 1. There's no unique solution. So this is under-identified. We cannot take the reduced form parameters and recover the structural parameters. Our knowledge of the reduced form solution, which we can get estimates of these things, is not enough to recover the betas. So if I wanted to know the elasticity of demand, I can't recover it in this system. The problem is that there's nothing to identify either equation. Let me show you what I mean. What we see in the data are just a set of equilibrium points. So this is one supply and demand, this is supply and demand, supply and demand, supply and demand. And from those equilibrium points, we need to figure out what the demand curve looks like and what the supply curve looks like. So all you see in the data are just a bunch of points that look like, whatever. From that set of points in the data, all these intersections of supply and demand, you have to find demand and supply. What you need to do that, let's suppose that, what am I going to put in demand anyway, just a second. Let's suppose that the demand equation has income in it. And then the supply equation is like it was before. In this case, when I shifts, it's going to map out the supply curve. So I can use changes in income to map out the supply curve. So as income changes, that will tell me what the supply curve looks like, because I'll move along the supply curve. So as long as I have a variable in demand that's not in supply, I can identify the supply curve. If I have some variable in here, which we'll do later, that's not in the demand curve, then as that variable moves, it'll shift the supply curve around and identify the demand curve. So in order to get identification, I need something unique in each equation to shift it. Now I have something unique. Here we said they depend upon U and V, but unfortunately I can't observe those. I don't know what those, if I knew U and V, I could identify it, but I don't know them. So that's not helpful. There has to be something in here that I can observe, that I can use to identify the demand equation. So what we're going to do is change the model to Q is alpha 0 plus alpha 1p plus alpha 2i plus u. That's demand. And the supply is the same as it ever was. So we're going to change the system to that. I'm going to claim that now this equation will be identified, and what will identify it are shifts in investment, or income, too much macro. And so as income moves around, it'll show me what the supply curve looks like. I've got an independent shifter here that will identify it, but I've got nothing in here to identify the demand curve. So the demand curve will remain unidentified. So the reduced form for this model, I'm going to skip the derivation because it just takes time and you ought to be able to do it yourselves by now. But here's the reduced form. Beta 0 minus alpha 0. This is what we actually would estimate. In the end, you're not going to have to be doing what I'm doing now. But this is so you can understand how to avoid doing this. So in the end, it's not this complicated to estimate, but this is the only way to understand what we're doing. It does this in the background. So we're going to call that lambda 0 plus lambda 1I plus E1. So now the reduced form will be a regression of price on a constant and on investment. And that regression is going to give me two pieces of information, lambda 0 hat and lambda 1 hat. Turns out those two pieces of information will let me recover two parameters. We'll get there. So this is the reduced form that we'd estimate. Then for Q, Q is beta 0 plus beta 1 lambda 0 plus beta 1 lambda 1 I plus B2. And I'm going to call that, again, Q equals gamma 0 plus gamma 1 I plus E2. So we'd actually estimate this equation and this equation. I promise not to go over today, so I'll look for. We're not quite done with this one yet, but I'll try to. So, estimation of the reduced form gives us lambda 0 hat, lambda 1 hat, gamma 0 hat, and lambda 1 hat. Can we recover beta 0, beta 1, alpha 0, alpha 1, and alpha 2? Well, generally the answer's got to be no. Because how many pieces of information do we have? 4. How many things do we need to know? 5. Not enough information to identify all the parameters. Something is unknown. But in this case, it turns out we can identify a subset of the parameters. We can identify the betas. And this is not something that's going to be easy for you to see. And so I'm just going to show you how to do it for this system. But here's how you would identify. If I take gamma 1 is beta 1 lambda 1. If I take gamma 1 hat, gamma 1 over lambda 1, what's gamma 1 equal? Beta 1 lambda 1. So what is gamma 1 over lambda 1? This is beta 1. So I can identify beta 1 like that. Beta 1 is identified. See, here's lambda 1, and here's the other parameter. So that divided by that is just beta 1. And I know that multiple. That's lambda 1. I get that from my estimate. I get this from my estimate. So I know that, divide one by the other, and I get beta 1. Now where do I get beta 0? Well, I know lambda 0, I know beta 1, I know gamma 0. So this equation here tells me that gamma 0 equals beta 0 plus beta 1 lambda 0. I know that, and I know that. So I can solve for that. So beta 0 hat would be gamma 0 hat minus beta 1 hat lambda 0 hat. This is just, all I did was just write down that equation. That equals that. To get the first one, you just almost always look at these and find something you can divide by something, and you use that piece of information to sort of back out the rest. There's no way for me to tell you how, you're not going to end up having to do this in the end anyway, so. Exactly how you find these solutions is not obvious. You just have to stare at them until you see them. But in this case, the betas are identified. So here's beta 1 hat, here's beta 0 hat, and so the betas are identified. And they're identified because of this I term. It allows us, it shifts around and identifies the supply curve. But there's no way to back out the alphas. You could stare at this all day, all night, work as long as you want. There's no way you'll ever identify the alphas. What we'll do next is we'll put R in here, which is probably rainfall. I don't know, we'll call it rainfall. Call it whatever you want. We'll put R in here, and we'll show that R identifies the demand equation. Once we have R in here, I'm going to have I'll have enough parameters to identify everything. I'll have enough reduced form parameters to identify everything. And so the R will identify demand, and the I will identify supply. Then we'll figure out how to do this without having to do this. So, okay, I promise I'd finish early, so 15 seconds.